Okay, so today is May 10th, uh, 2021, and this is lecture 17. So let's get started. Okay, um, what we did last time, we discussed the periodic excitation, and what we said was that the if you have so this was what we discussed periodic excitation, and as we saw, the general formulation resulted in this, that if you have a damped system subjected to a forcing function which is periodic, we ended up with the formulation that you had the u of t would be a naught over k plus the summation of n going from 1 to infinity of uh, b a n, okay, cosine n omega t minus phi, okay, plus bn sine n omega t minus phi, okay, divided by k times h, okay. So we are going to demonstrate that uh, the application through simple problem. So let me uh, set up the problem. This is the problem that I wanted to do last time, and we couldn't finish it. So let's do it. This was the example problem. We had a system consisting of a mass supported by a spring and a damper and another um, spring attached to it. And this is spring, let's say this is K1, this is K2, this is C, is connected to a piston, and this piston is going up and down uh, through the action of a cam driver. So this is a cam driver rotating at the frequency of 60 RPM or 2 pi radians per second. So it is inducing a motion to this system, which is basically an input displacement. Okay, so this is a system subjected to an input displacement. That input displacement, the function is given like as this. It is a sawtooth function. The maximum displacement, which is this is y of max, so this is an input displacement. Okay, this y of m is given as 25 millimeter. So this sawtooth function it goes like this 0, 1, 2, 3 in terms of the second. So for the first period of this function, which is what we need, this function is described or given as, or we given that the what we call, as you remember, cam lift as 25 millimeter. So this function is described or can be described as 0.025 t. So the magnitude of the mass is given. Fortunately, this is all in metric, 20 kilogram. K1 and K2 are equal, each 3.5 kilonewton per meter, and the damping coefficient is zero point 0.2 kilonewton second per meter. Okay, so we want to find or set up the displacement function, or in other words, find the displacement that this mass experiences due to the action of this input displacement. In other words, the relative displacement of this mass with respect to this fixed base. Okay. Any questions as far as the problem description or the details of the problem before I go any further? No? All right. So let's see. When we have a periodic excitation, there were two steps involved. You remember that? Step number one, to set up the forcing function for the first period of this excitation. We have the displacement function given. Forcing function is, you can see that obviously from the general formula for functions subjected to input displacement was what? Mu double dot, this was the equation of motion. Cu dot plus Ku was, on the other side, was K2y of t. So this is our forcing function, okay? If you go back to your notes for the input displacement, you will see that we had derived this equation. So f of t would be simply K2, which is 3.5 kilonewton per meter times y of
Professor,
t. Yes.
could you move your page up a
Oh,
little?
sure.
Thank you.
Here we go. Sorry. All right. Is it also visible as far as the resolution goes? Okay. So convert this to Newton per meter to make it easier. So we have 3,500 times 0.025. T is going to be 87.5 T. So this is the forcing function for the first period. So the second step involves now what? Converting this function, forcing function, into a Fourier series expansion. So you need to evaluate the coefficient of the Fourier series. A naught was 1 over the period integral from 0 to t of f of t dt. So let's just substitute for that. The t is the period here, which is 1 second. So t is 1 second. So we have 0 to 1, 87.5 t, which is the forcing function, dt. So just a simple integral would be what? 87.5 t squared over 2, evaluated from 0 to 1. So if you evaluate that, you get a naught that comes out as 87.5 divided by 2. So this is the first coefficient of the Fourier series. Okay. Any questions? No? All right. So how about AN? AN
Wait,
was,
actually, yes, Professor. Why
yes,
is it 87.5 now?
because you see, this is the integral, 87.5 t squared over 2. So you just substitute for 1. So it becomes 87.5 over 2, right?
I see. Thank you.
Sure. So AN would be 2 over the period integral from 0 to t of, you remember that, would be f of t times cosine of n omega t. So you have 87.5 t cosine n omega t dt, where, remember, omega is 2 pi over t. T is 1, so omega in this case is just 2 pi. So let's perform the integration. If you remember, of course, we can take and this is 1, so you can take the constant term out. So you simply have 2 times 87.5 times this forcing function, 0 to t or 0 to 1 of t cosine of n omega t dt. Does this integral look familiar? If not, I refresh your memories. This is integration by parts. You remember integral of uv dt is uv minus v dt. You remember that? If you don't, that's fine. It's going to require about a few steps of integration. I don't expect you to remember that, and neither do I want to go through that because this is not a course in calculus, it's a course in vibration. So you just need to find what is the outcome of this integral. So you can look up the integral tables, and you see that this would be 2 times 87.5. The result of this integration would be 1 over n omega squared cosine n omega t plus 1 over n omega sine n omega t evaluated from 0 to 1. Okay, so let's do the substitution.
Professor, can you show the bottom of that page real quick again?
Sure. Here you go. That is the integral, this integration by part that has been evaluated. So that's the result of this integration. Okay, so all I need to substitute for these bounds of integration, and you will see that it comes out, an would come out to be 2 times 87.5. Substitute for n omega, which is 2 pi. So we have 2 pi, 2 pi t would be 1. Okay, so this would be 1 minus 0, which is also cosine of 0 is 1, plus sine of 2 pi omega t, which is 0. So an comes out to be 0. I'm sorry, so that, yeah, the an. Any question on that? Now, the last coefficient, Fourier coefficient is bn. And bn was 2 over pi, the integral from 0 to t of f of t sine n omega t. Sine n omega t dt. And that would be what? 2, again, times 87.5 comes out. T is 1. Integral from 0 to 1 of t sine n omega t dt. Again, doing the integration by part and substituting for omega, which is 2 pi, will result in b, that bn would be 2 times 87.5 bracket 1 over n squared omega squared sine n omega t minus 1 over n omega cosine n omega t from 0 to 1. You substitute for that, you get 175, negative 175 times 0 minus 1 over n omega minus 0. So bn would come out to be negative 175 over n pi. So this series expansion, Fourier series expansion, we have only a 0 and Bn.
Is it positive because the two negatives cancel?
Let's see. No,
Or
no. I actually, I prematurely, I took this out.
oh, gotcha. Okay.
Yes. So it's negative.
Okay.
So now, what is the response the general response under periodic excitation is A0 over K, where K is the stiffness of the system, okay, plus summation from n to infinity, in other words, infinite terms of the series. An is 0, so I don't even write that down. We have only Bn over K times sine n omega t, okay, minus phi times h. Phi is the arctangent of 2n zeta r, 1 minus r n squared. And h was 1 over 1 minus n squared r squared, okay? You remember from h plus 4 zeta squared n squared r squared. So this is the function, a frequency response function. So all I need to do is basically substitute for the numerical values of these terms. K, in this problem, you can see that the two springs are in parallel. So K is K1 plus K2. So that would be 7,000 kilonewton per meter. I need zeta. Zeta to substitute in this equation is damping coefficient of the critical damping. Damping coefficient is given as 0.2. Critical damping is what? 2m omega n. Omega n is what? Is k over square root of k over m. M is square root of m times square root of m. So this becomes 0.2 over 2 square root of k m. So substitute for k and m, 0.2, 2 square root of 7,000 times m was given as 20 kilogram. So zeta comes out to be 0.267. Any questions? I also need omega n here because R is the ratio of omega over omega n. Omega n is K 7,000 over M 20. This comes out to be almost 18.7 radians per second. Therefore, R, which is omega over omega n, would be omega was 2 pi over 18.
Can you shift your paper a little bit?
Oh, sorry. So this is omega over omega n. That would be roughly 0.11 pi. So that's R. So I would substitute all these values in that to that equation, and U of t would be 87.5 divided by 2 divided by k. 87.5 point over 2 was a sub 0. So this is a0 over k. Okay. Minus bn was negative 175 over n pi. So I take negative 7 over k, of course. So I take this part out of the summation, that would be 175 divided by 7,000 pi. This is k, bn over k. Now, summation of n from 1 to infinity of sine of 2 pi n t. 2 pi was omega n t minus phi divided by that is square root, which is 1 minus 0.11 pi squared. That's nr squared minus 4 zeta squared 0.267 times n times r squared. Okay, so you need to evaluate. Of course, phi is the arctangent of 2 zeta n r over 1 minus r squared. So you need to substitute for that to find the value of phi that goes here. So if you perform this, you can perform this for whatever number of n terms you want, let's say 3 to 5 terms, in order to find the value of the displacement that in this. Okay, I don't think I have not done that for a particular value, but if you want, you can just use, say, 3 terms and find the value of this summation, and then you have the displacement of the system due to this forcing function. Okay, any questions?
Yeah. Wouldn't the bn that we had solved for earlier have a 2 pi in the denominator and not just pi?
Bn was negative 175 over n pi, right?
Well, originally it was omega, right? And I thought omega was 2 pi.
Omega was 2,
Right before you.
Oh yeah, just above that.
right here, you mean?
Yeah, where you do
To the right.
5 times negative 1 over n omega.
Oh, n pi I have here.
Yeah, so shouldn't omega be replaced with 2
Oh, I
pi?
see what you mean here. Yes, that's right. You're right. This is 2. So this would be over 2. So in other words, I have a factor of 2 here. Thanks for the correction. Yes. So there will be a 2 here.
All right, thank you.
So these periodic excitation problems, as you can see, they're kind of messy. A lot of sort of mathematics is involved, and you end up with a series, basically summation, that you need to find its value. And it needless to say, you cannot do it by hand. You have to use something, whether it's a Excel or MATLAB or whatever tools, in order to find the answer. That's why I'm not gonna do another problem, because they're if you look at even the homework problems that I have assigned, give or take, they're very similar to this, and it all comes down to evaluating basically this function. That's it, in order to find the response of the system. And once you find the response of the system, in this case, obviously, would be a sinusoidal function. So whatever is the magnitude, the amplitude of that sinusoidal function would be your maximum value of the response. Plus, of course, this constant term.
Is n only odd terms or even terms as well?
Oh, in this case, if I'm not mistaken, actually, good question. Because sine of if n is odd, let's say is 1, okay, So you have sine of 2 pi. So it should be, no, it can be both actually. So it would be 1, 2. So,
Okay.
Yeah.
Okay. Thank you.
sure. Any other questions? All right. So with that said, let's see where we are as we have done this before. So this is what we have covered so far. We've been discussing forced vibration. So we discussed harmonic excitation, which of course consisted of 3 different topics: pure harmonic, rotating unbalance, or input displacement, which may be harmonic. We covered now periodic excitation that is also came down to the same problem, which is harmonic excitation, by converting the general periodic function into a series summation of harmonic terms. The problem is reduced down to harmonic excitation. Now, what happens if the forcing function is not harmonic or periodic? How do you find the response of the system under a general excitation, okay, or an arbitrary excitation? The type of general excitation that I can think of, for instance, are blast loading or impact loading or things of that sort, or even, some more complex loadings. But that's the question. How do you find the response of the system when you have a general excitation? In other words, let's say you have a forcing function like this, which has an arbitrary shape. And how do you want to find the response of the system under this function? This is what we do. If I divide this into small segment of time, okay, and consider, okay, one of these strips. In other words, let's say you consider this forcing function at an arbitrary time tau, okay, and you look at this function being made of basically infinite sum of these divisions, right? If you recall so in other words, if the value of this function at that time is t, now let's look at this problem. Let's assume that we are only going to consider the action of one of these forces, the force at any arbitrary time that is acting on a system for a very short duration of d tau. So if this is f of tau acting during a very short duration, you remember the definition of impulse. Impulse is a force times a short duration of time, okay? And you remember from dynamics, when you have an impulse load, that is a forcing function that acts at a very short duration. For those of you who are maybe more math savvy, what is this function? Is a delta function, right? Direct delta function. But I don't get into that. For the time being, all I want you to remember the concept of impulse. Impulse, if you remember from dynamics, causes an increase. All it does, it causes an increase in momentum. Okay? That is f of tau, d tau, is basically the change in the momentum of the system. Since, of course, mass assumed to be constant, doesn't have to because it's a general term, but general concept, you can rewrite this also as this, m, okay, change in the velocity. So this is the general formula or the general expression for second law of mechanics. What does it say? It says, look at this. What is that? This is rate of change of momentum. So rate of change of momentum of a mass, okay, is equal to force acting on the mass, which is this, okay? And this force is what? The force is, if I rearrange this, would be d with respect to tau of m u dot, okay? So f of tau, okay? This is the second law of mechanics or second law of Newton in terms of momentum. And of course, you can rearrange this, given that mass is constant, but you get f tau d tau over m is equal to d with respect to time of du. So this is another alternative form of writing the same expression, but it's a very important and very informative form of that expression. What does that mean? This means that, and I will write that down, that as a consequence of the action of this impulse load, okay, what do we get? We get a change in velocity. That's what the right-hand term is. So due to action of an impulse load, what results is a change in the velocity. So what's the big deal? So let's now pause and focus on the problem that we have in hand, what we said was that we consider an impulse load acting on this system, okay? So we do have an impulse load. So this, okay, causes a change in the velocity, right? In other words, the system has been addressed to begin with. And when we have an impulse load, all it does is causes a change in the velocity. So impulse, all it does represents an initial condition. System was addressed, right? That means the initial velocity was zero, the displacement is zero, but the initial velocity is what? Is now F tau d tau over m. Okay? This is it. This is a change in the velocity, right? This change in the velocity is this. So the problem that we have in hand then is a free vibration, okay, with given initial conditions. You remember the solution to the free vibration of a system on the, under given initial conditions for only the case of underdamped systems, which all we care about in all these studying of mechanical vibrations, because that's the most common type of system. If you go back to your notes, you see that the response of a system, an underdamped system, freely vibrating with the initial conditions given, was this: e to the minus zeta omega n t, okay, zeta omega n divided by omega d sine omega dt plus cosine omega d t times initial displacement plus sine omega d t over omega d times initial velocity. This was a general formula we derived. If you go back to your notes, for underdamped system, this was the response of a free vibration of an underdamped system due to initial conditions. But this is zero because these are the initial conditions we have. So we don't have that term. So therefore, the response is only this: e to the minus zeta omega n t f, okay, if I substitute for this, f d tau over m times 1 over omega d sine omega d t. So what is this? This is the response at t is equal to tau at a specific time that we considered when an f of tau, that force, acts on the system. Okay? So this is at t equal to tau, right? So in other words, we have a system. This force at time tau acts on this system, okay? And this is the response at that time. So what happens if you want to find the response here, which is what? If this is t Okay. Right after this, in other words, at the time t minus tau, after this forcing function or the impulse happened to the system. Okay. Would be obviously, you can easily find it from here, right? Would be u of t, u would be f of tau over m. So I'm just rearranging this times 1 over omega d. Okay. So I'm saying that we want to find at t minus tau, at a different value of time now. So this would be e minus zeta omega n t minus tau sine of omega d t minus tau. Okay. So at any arbitrary time, t minus tau, after this impulse acts on the system, this is the response of the system at that point. But wait a minute, what is the problem we have in hand? We have an infinite number of these impulses that are acting on the system. In other words, our problem is this. We have all these impulses, right, that are acting on the system. So what do I need to do? I need to evaluate an infinite sum of all of these, meaning an integral going all the way from the first point, which is 0, that the first impulse occurs, all the way to a general time t. So all I need to do, just do what? Right? U of t, which is this, the response of due to all of those impulses would be m and omega d are constant, so come out of that integral. So you need to perform integration from 0 all the way to an arbitrary time t of f of tau e to the minus zeta omega n t minus tau, okay, sine of omega d t minus tau d tau, okay? This is called Duhamel integral or convolution integral. For those of you who are familiar with the concept of convolution, that's what we did by looking at the effect of those individual direct delta functions and add them up. Basically, that's what we've done. So forget about, of course, all the mathematical derivations we did. Evaluation of the response under the action of a general loading function comes down to this, that you write the function that you're given, okay? And you do consider a dummy variable if you want to basically have a procedure for solving the problem. Dummy variable tau. And you perform this integration, integral from 0 to t of f of tau e to the minus zeta omega n t minus tau t minus tau sine omega d t minus tau d tau. So the variable of integration is tau. So in this integration, when you're performing this integration, this is your variable. And t will be obviously considered as a constant value or a number. But the outcome of this integration would be in terms of t, which is time. I'm going to spend some time on this, and we'll see how we evaluate this integral. It's not easy, but we will see through several example problems how you do that, and then I would introduce actually a general table for evaluating the most common Duhamel integrals for the most common types of loadings that you have. But the good news is we will spend most of our time solving this problem for the case of no damping. So when damping is 0, obviously this would be 1, and omega d becomes omega n. So for this case, u would be what? 1 over m omega n 0 t of f of tau sine omega n t minus tau d tau, which is a much easier integration to perform. So since we are out of time, I'm going to stop here. See if you have any questions. We are going to spend several sessions covering this concept of Duhamel integral.